Hello scholars, welcome back to iOS YouTube channel. So today class, we are going to look at Marshallian or uncompensated demand function. So you can call it Marshallian demand function or uncompensated demand function. Now, why is it called Marshallian? Why is it called uncompensated demand function? So we have this function under consumer behavior. So we have uncompensated demand function in a situation whereby the income of a consumer does not change as the price of the goods change. That's why I say it is uncompensated for. You know, it's different from a situation whereby as the price of the goods and services change, or a price of commodity X and commodity Y change, then income of a consumer also change. In that situation, that means the total utility of the consumer will remain unchanged, because as the price change, the income change too, which reverts to as a real income. Do you understand? But now, in Marshallian and uncompensated demand function, as the price of the goods change, the income of the consumer does not change, and which leads to what we call substitution effects and income effects. But we are not interested in substitution effects and income effects. So we are interested in derivation of Marshallian or uncompensated demand function. So I'll state the reason why it is called uncompensated, because the income of the consumer does not change as the price of the commodity change. So now, this is the equation given to us. We have the first equation, which is known as equation 1, is this, and this will represent our equation 2. Now, looking at this equation 1 and 2, this is the utility function, and this is the budget line. Let me repeat myself. This is the utility function, and this is the budget line. Don't forget that we have optimum or maximum utility function at a point whereby the budget line is tangented with the indifference curve. So I hope you guys understand that. Now, this aspect is just a derivation aspect. So now, looking at this now, this is our objective. Note, this is our objective. The equation 1 is our objective. The objective is that we want to maximize utility. But our objective is subjected to the budget line. That is, our objective is constrained by the budget line. What are we saying is that what can determine your utility satisfaction is the level of income, what you can afford, which is the budget line. So this is the constraint now, and this is the objective that we want to achieve. So now, by deriving this thing, for us to derive the Marshallian or uncompensated demand function, we start with some steps. So if you have this question and you have to derive the Marshallian demand function, the first thing I want you to know is that this MO that is here, you know, is known as income. This is our income. Why? This, the price of X commodity X plus the price of Y commodity Y, this is known as our expenditure. Sorry, mind you, it is known as our expenditure. So this is my income. This is known as our what? Expenditure. So in a situation whereby income and expenditure equals, then is a function of utility maximization. So I just want to state that. Now let's solve the question. In solving the question like this, the first steps you need to take is I know that you know that we are using the Lagrangian function. So the first step is step 1. State the Lagrangian function. State the Lagrangian. So now you state the Lagrangian. Then what is the Lagrangian function? The Lagrangian functions will now be the combination of the objective function and the constraints. The sum, let me put it that way, the sum of the objective function and the constraints. So then my Lagrangian function will now be L. I represent Lagrangian as L. We have Lx, Y, which is commodity X and commodity Y. Then, you know, I said the sum. You know, the commodity X and Y is my objective function. That's why I said the sum. Then plus, using the sum with what? With the constraints. But in this case, you will add what we call lambda here. This sign is known as lambda. Then you open the brackets, then you insert your what? Your constraint. That's why I always categorize as sum. So that when you want to state your Lagrangian function, you know that Lagrangian function is the sum of the objective function and the constraints. And this is our constraint, the budget line, and our objective function is our utility function. So now we want to add it together to form our Lagrangian. But what makes it to be unique is that we need to add this lambda to it. If you don't add this lambda to it, you are getting it wrong. So what you need to do now, you now have your MO minus PXX minus PYY, then you close the bracket. Now, I'm sure that you'll be asking yourself a question. How do I write this from this minus, because what we have here is this. So what we have to do here is that we arrive at MO minus PX of X minus PY of Y. We arrive at it by collecting the lag time, by make this one to equals to 0. So we make the constraint to equals to 0. That's why we get this. So what do I mean? let me put notes here. I want you to note that we arrive at this point. I want you to know that we arrive at this point because we make MO, minus MPX minus PY equals to 0. So we make this one to equals to 0. That's why we can get what we make as sum here. So I want you guys to get it. I want you guys to get it right. So I hope you are getting it. So we are still under the step 1. Then the step 2. Let's move to the step 2. Step 2. The first step is you stating the Lagrangian function. And this is the Lagrangian function here. Then the step 2 now is using first order condition. Using first order condition. So when we are talking about the first order condition, that is we need to find the Lagrangian dx, then we equate it to 0 as a first order condition, then the Lagrangian dy, we equate it to 0, then the Lagrangian the lambda, we equate it to the 0. This is what we mean by first order condition as the second step you need to take when you are deriving this. So moving on, let's find the first order condition. That is, now I'll need to find my Lagrangian dx, then which means we are applying the partial differentiations to this. So the Lagrangian dx, this is my x. Automatically differentiating this will give me 1. So 1 times y, I will have y here. Then let's move on. So if you use this Lagrangian to open this bracket, so if I use Lagrangian to open this bracket, that means I'll be having, if I use this lambda, it is lambda. So open that means I'm having lambda multiplied by this, lambda multiplied by this, then lambda multiplied by this. So now we need to differentiate it. So I'm just breaking it down. I don't just want to give you the final answer like that. So now, by doing so, I'm having lambda MO minus lambda PX of X minus lambda PY of Y. This is what I'm going to have. Then differentiating this, because we are dealing with partial differentiation, automatically this lambda MO will be 0 and this one will be 0 because we refer them as a constant, because the X that I want to differentiate is not part of it. So where in all this value or in all this variable that we cannot find the X that we are differentiating, then it will automatically equal to 0 according to partial differentiation. Now I'm left with this. So in this one I'll be having lambda px of x, because automatically lambda mo is 0, lambda py of y is 0 because we don't have x there. But now this one we are left with lambda px of x. So are we having lambda px of x? That means this is x that I want to differentiate. And differentiating of x will give us 1. That means we are left with what? Minus lambda px. Minus lambda px. That's what we have. So if you count down and go through this thing and do it partial differentiation, this is what you are going to get. And this is equals to 0. Are you following? So now let's proceed. So we are done with the lambda dx, then the Lagrangian dx, then let's move to what? The Lagrangian dy. So differentiating the Lagrangian dy, I'm sure that we have x here minus lambda py equals to 0. That is what the differentiation of the Lagrangian dy, because this is y, this y returns to 1, multiplied by x, I will have x here. Then the same thing, this will return to 0, 0 because it's a constant. But here we now have what? Minus lambda py, because this y here will be equals to 1 and we multiply it. I'm sure you understand the differentiation I'm talking about. So let's move to the next one. Then we have the lambda, the Lagrangian, sorry, I'm just saying lambda. It is the Lagrangian, the lambda. So the Lagrangian, the lambda is, I have issues with this. So to differentiate Lagrangian, the lambda, so automatically lambda is not here. What is here is 0. So then I'm left with this. So by left with this, that means we want to differentiate lambda and this. That means, and if I differentiate lambda, lambda will give me 1. 1 times what's inside the bracket, I'll get what's inside the bracket. Therefore, I'm having this MO minus PX of X minus PY of, of Y, which equals to what? 0. We have to be giving all these things an equation. We have to do this equation 1, equation 2. This will be equation 3. Sorry. This will be equation 3. So if we have that as equation 3, then this will be my equation 4. This will be my equation 5. Yes, this will be my equation 6. I hope you are getting it. So that, because I'll be referring to that equation as well. I want to state equation there. So let's move on to the next thing. So the next steps now, let's say this is step 2. Then let's move to step 3. So in step 3, make x, y, and lambda, make x, y, and mo as a subject. So in terms of we making them as a subject, that means y, because I want to make it as a subject, this my friend we move to this side. This my friend, we move to this side. Then this my friends too, we move to the other side. So let's do that now. So that means in this case now, I'm going to have y equals to lambda px, okay? Then this will give me equation 7. So then, in other way around, x will also equals to lambda py, which is will give me equation 8. Then my MO will equals to what? Px of x, plus py of y, which this will give me equation, this is equation 8. Then this will give me equation 9. This will give me equation 9. So I think you are getting, that's why I have to break it down step by step. So let's continue here. We have to continue here. So since we are here already, then the next step you need to take, let's say step 4. Now, our step 4 now is take the ratio of equation 7 and equation 8. Take the ratio of equation. So what is in equation 7? This, I'll be having y equals to lambda px, then over x equals to lambda py. So what I have interest in delineating here is the lambda. Are you communicating? Sorry, am I communicating? So what I have interest here is, eliminate the lambda. So, and by doing so, once I eliminate the lambda, I'll be having y over x equals to px over py. Then you cross multiply, then y will equals to px x of x, because this will multiply this, then py. So we are getting this. We are getting there small. Then let's make clean this. So now once I get this is not my actual y. This is not my actual commodity y. Once I get this, then yes, that's equation 9. So the next step is step 5. You say that substitute y in equation 9. Substitute y in equation 9. And what is equation 9? Equation 9 is MO equals to pxx plus pyy. So this is equation 9 that I want to substitute. So in that case, let's clean this. Since I want to substitute it in equation 9, then let's put this guy there, which is what? P of xx, then py. We have this. Automatically, this will cancel this. Hope you are getting it. So if this cancels this, then MO will equal to what? Px of x plus Px of x. Then this is going to give me 2Px of x. So we have this. But our aim is to get the Marshallian function of commodity x. So, and this is the commodity x. So what am I going to do? Divide both sides by px, 2px. Then this cancels this. That means x equals to MO of 2px. So this means Marshallian function of commodity x. So this is the Marshallian function of commodity x. Now we need to find the Marshallian function of commodity y. So, and in finding Marshallian function of commodity y, we can easily substitute x in this function. So we can easily substitute x in this function. Can you see? So we can substitute this x here. That's what I'm saying. So that we can get the Marshallian function of commodity y too. So let's do that here. So what we are going to do here is that we have y equals to p of x over y. Then what's this one? My x is now what? MO over 2px. So, and we having this we cancel this, then y will equals to what? MO over 2py. So this is also Marshallian function of commodity y. So this is also Marshallian function of commodity y. Now, moving on, what if there's another advanced way they can ask you a question under this Marshallian and uncompensated demand function? What if the question state that? The question might not even state that you should find the Marshallian function of the two commodities. The question can tell you that find the indirect utility function. Indirect. So in that case, if you are asked to find the indirect utility function, so the indirect There's no how, if the question tells you to find the indirect utility function, there's no how you not find your x and y, you find it already. So the indirect utility function will now be, we represent that one as v, will now be x, y. Then what's the value of the xy? The value of the xy is what? What's my x? Mo over 2py. Then, sorry, I made a mistake here. This is supposed to be y, sorry. This will be Mo over 2px for x. Then here, multiply by Mo over 2py. So we having this Mo over 2py, then our final answer here will now be for the indirect utility function. Sorry, let me clean this. For the indirect, so our final answer here will now be v will now be equals to what? Mo, square over 4px py. So if the question states that you should find the indirect utility function, then this is your final answer. So I hope by the step-by-step explanation given to you, you guys understand how to derive Marshallian and uncompensated demand function. Here, see you in the next video. In our next video, I will be explaining the Increasing or compensated demand function, which serve as the opposite of the Marshallian. So thank you. Thanks for watching. Make sure you subscribe, share it, like, and comment. God bless you.